have a spherical shape to it with the highest probability. Those dots represent what probability closest to the nucleus. N equal 1, I'm going to put that down at the bottom.
I can't write fast enough.
N equal 1. So lowest, most stable. Every atom, therefore, has actually 2 electrons, just hydrogen, in the N equals 1 level. So this one here is called 1s. 1s. Assumption. It holds 2 electrons. So a hydrogen atom has 1 electron. And we're going to denote that with a little arrow here, and I'll explain why arrows in a minute. That's the hydrogen atom. That's where the electron for the hydrogen atom is. How about helium? Helium has 2 electrons. Where do you think the other electron for helium goes? Helium holds. We can put 2 electrons here. We're going to put an arrow here going the other direction. Again, I'll get to that in a second. That's helium. That's what we call the electron configuration for helium. Now, if you look at the top of the periodic table, how many elements are in that top row? 2, right? Hydrogen and helium. That means we go to the next atom in the periodic table, which is lithium, right? You can't put an electron in there. You have to jump to the next highest quantum number, which is N equals 2. It's a big energy jump. This shell is what we call is now full. The helium shell is full, and that's why it's a stable state. If we need to put another electron like helium as we start going up the periodic table, N equals 2, 3, 4, we got to put electrons in higher energy level. And that's a big jump. So let's take a look at the N equal 2. That's all you can do with N equal 1. N equal 2, there are 2 different subshells, an S and a P. Let's do the S first, and that's called a 2S. It looks similar to a 1S, it's a spherical shape, only it's the electron probability method that goes a little further out from the nucleus to the 1S. And in a minute, we're going to look at a cross-section of this thing to show what that probability looks like. Very similar to the 1S, but bigger. Also holds 2 electrons. So, what's the next, after helium, what's the next atom? Lithium, right? We'll put it as a lithium. 3 electrons. What comes after that? Beryllium. Beryllium, yes. There's 4 electrons. There's beryllium. Can't put any more here. Okay, that's all you can hold from it anywhere. So the next one we're going to go to is 2P. And notice in the periodic table, we're going to jump clear across to the right-hand side. We'll clear across to the right-hand side. 2P is completely different. The P is completely different from the S. First of all, there are 3 of them, 3 different equal energy levels, each holding 2 electrons. So the 2P is something like this. 3 of them. Each holds 2 electrons. 6 electrons total. How many columns over there in that right-hand side of the main group? Starting with boron. 6. Yes, indeed. So if we were to fill this thing up, starting with boron, putting electrons in it, we'll show you how to do this in a bit. A specific way of doing it. When you get it completely full, it'll be a neon. And now, the N equals 2 is full. If I put all 6 electrons, 2, 4, 4, 6, 8, 10 electrons. There's neon. Noble gas. Full principal quantum. If I want to go to the next atom, which would be sodium, I have to jump up to another energy level, n equals 3. Now I got to go to n equals 3. Here's the, I mentioned about a cross-section of these orbits. The mathematics of this thing from the Schrodinger wave equation shows you how peculiar these appear. Remember we said these are probability maps. So it says there's a very high probability that the electrons will be found here or out here, but 0 probability of finding an electron in between. And so if you think of an electron as a particle, it sounds kind of weird. How can it be here and here, but it never goes, how can it go from one to the next? It's never there. It just doesn't make sense. However, if you think of the electron as a wave, then you can think of these like ripples in a pond. You put a pebble in it and the ripples spread out. It's more like a wave kind of behavior. That's part of the peculiarities of quantum theory. The peaks, and we said there's 3 of them. They're not spherical at all. They have these funny little dumbbell shapes. And they go in the 3 directions, X, Y, and Z. So there's 2 electrons in this one, 2 electrons in that cloud, and 2 electrons in that one. That's when they're full. All 3 have the same energy, which is why I show them as 3 lines like that, the same energy. Now let's look at all the shells and subshells, okay? How they work. We only did the n equal 1 and n equal 2.
Huh?
Principal quantum number and subshells, SPB and n equal 1 is only a 1s. That's it. 2 electrons.
I can't do it actually. I was going to try to use this, but I can't.
2, you can only have S and P, which is 2 plus 6. 2 electrons go. When n equals 3, you now introduce the d subshells. We're going to show that in a minute. 2 plus 6
Plus 2?
equals 10. Anything above n equals 3, 4, 5, 6, 7, you have the S. We'll talk about that. That goes that goes. So those are the only ones that you can have. So you don't have any 1Ps, no 2Ps. So if you think of it in this way, just remember S, P, D, F. N equal 1, 2, 3, 4 above. I have them all. So this is the n equal 1 is the S, n equal 2 is the S and the P, n equals 3 is SPD, and 4 and above, got them all. The S has only 1 energy level, put that here, 2 electrons. The P, 3 energy levels, 6 electrons. The D, 5 energy levels, 10 electrons. The F, yeah. Top row of the periodic table. How many elements up there?
3.
Hydrogen.